dynamics. Thanks.
So the usual questions, can you see my slides? Can you hear me well?
Yep, everything looks good.
Okay, perfect, thank you. So good afternoon, everyone. As David said, my name is Ariane Weber and I'm a PhD student in the Transmission, Infection, Diversification, Evolution short TIDE group in Jena, which is led by Denise Kühnert, for whom I'm filling in here today. So the next 25 minutes, I would like to give a very short overview of one method that models or that uses epidemiologic as well as evolutionary modeling, and how we've used it to gain further insights into the transmission dynamics and evolution of SARS-CoV-2 in two different application examples using phylogenetic reconstructions from whole genome SARS-CoV-2 sequences. So phylogenetic reconstructions usually are represented in tree structures like this, which are generated by a mutation process and represent or illustrate the evolutionary relationship between the samples. Now, for fastly evolving pathogens like viruses, mutation events happen on a similar time scale as transmission events, so that this evolutionary tree can actually be assumed to be a good approximation of the underlying transmission tree. So therefore, starting from genetic data or using genetic data to infer an evolutionary tree, we can also characterize the underlying transmission network. And in what I'll be showing today, we're doing this in a Bayesian framework, which means that we sample in an MCMC framework from a posterior distribution of trees. This posterior distribution, which is shown here on the bottom, is proportional to the product of the likelihood in the prior distribution. The likelihood is the phylogenetic likelihood, so it depends on the substitution as well as the clock model, and it therefore kind of scores how well the sample tree fits the evolutionary relationship between the samples. Now, the prior distribution, on the other hand, among other things, scores how well the sample tree fits a specific transmission process, and it does this by calculating the probability of the sample tree under a specific population dynamic model, and this is this term here. And for the population dynamic model, what we're using and what I'll be presenting today is a birth-death sampling process as it is implemented in the BEAS2 package BD-SKY. This model is defined by three parameters, being the transmission rate lambda, the death rate mu, and the sampling rate psi. As a tree generating process, it can be visualized as I'll be showing here on the left. It starts at time t equals 0 with one infected individual. At every point in time, infected individuals can transmit the disease with rate lambda, leading to branching events in the tree like here or here. At every point in time, infected individuals can die with rate mu, leading to ends of a branch that is tips in the tree, as you'll be able to see here on the green tip. Death here does not necessarily mean real physiological death, but just not infecting other people anymore. And if we look at the upper part of the tree, we can also see a sampling event happening here, which is denoted by this black circle and is connected with the removal of the infected individual from the population of infected. Now, of course, this process does not evolve in this kind of branch-like manner that I've just shown it in, just for illustration purposes, but it evolves continuously through time, leading to a tree structure like this. And if we now want to re-estimate this tree structure from sampled individuals, which would be the black dots at the tip of the tree, we're not able to reconstruct this full tree, but only the so-called sample tree, in this example, looking as you can see here. So we can reparameterize this model to quantify more intuitive epidemiological parameters, namely the effective reproductive number, the recovery rate, and the sampling proportion. The effective reproductive number being the number of secondary infections from one infected individual in a non-naive population, the recovery rate being the inverse of the duration of infectiousness, and the sampling proportion being the probability of a lineage being sampled. So here on the bottom, you can see how this reparameterization looks like, and this shows that these three parameters are interdependent. So we won't be able to estimate all three of them at the same time, but we always have to fix at least one or two of those. And then all of the analysis that I'll be, or basically the two application analysis that I'll be showing today, we always at least fix a heavily constrained recovery rate. So if we have a scenario like this here, so where we have one connected outbreak, we can go ahead and infer one connected tree together with the epidemiological parameters from it. But if we now turn instead of one outbreak, which is this basically epidemiologically defined setting, to a more locally defined setting, so being, so for example, a region during a pandemic, so considering the SARS-CoV-2 pandemic, if we look at a specific region through time or at a specific point in time, the picture that we usually have epidemiologically is not just one single connected outbreak, but multiple independent introductions into the area forming their own transmission chains. So we don't necessarily want to reconstruct one tree from all of those samples if we want to characterize the dynamics within the region, because a big part of the reconstructed tree, which informs the epidemiological parameters, would lie outside of the area. So what we do instead is that we define genetic clusters to approximate these transmission chains, and then infer trees for those genetic clusters linking the epidemiological parameters. Now this means that we assume each of these trees to be an independent realization of the same stochastic birth-death sampling process, which again must not necessarily be a good assumption, because again, considering the SARS-CoV-2 pandemic, we know that there are certain regions or certain time periods where where different variants spread at the same time in the same region, which showed differences in the transmission properties. So for example, transmission advantages or transmission disadvantages, which would basically, which could, for example, be the variants of concern that we're currently seeing. So for this, we introduce a scaling factor denoted here by R into the model, and the scaling factor being the transmission rate scaling factor quantifies the relative difference of the transmission rate of the specific cluster compared to a baseline cluster, here being, for example, the blue cluster. And of course, we can also combine this with changes to time. So we can set specific points in time at which either one, some, or all of the parameters are allowed to change. And then starting from the sequence data set from which we want to infer the tree and the epidemiological parameters, when we have one connected outbreak, we can go ahead and generate a multiple sequence alignment fit for phylogenetic inference, and then define our evolutionary model setting and our population dynamic model setting to then infer the tree as well as the epidemiological parameters. Now, if we have the setting of multiple independent introductions or multiple independent transmission chains, we first have to define the genetic clusters for which we want to infer different trees, and then we can again define our evolutionary as well as population dynamic setup. So turning now to the application of this method to SARS-CoV-2 genomes, I would like to show two examples of data sets from Germany, which represent epidemic settings from different epidemic settings, also from different time periods. So as a very broad time and epidemic contextualizations of these examples, we can have a look at this very rough sketch of the COVID-19, the basically German COVID-19 timeline. The first diagnosis of COVID-19 in Germany was made at the end of January 2020, and then the following weeks and months showed the first bigger outbreaks due to different introductions into the country. And this is already the context of the first example that I want to present, being a data set of sequences from the so-called Heinsberg outbreak, which was one of the first bigger outbreaks in Germany, facilitating the seeding of the epidemic in the country. So during 2020, there was not yet any countrywide systematic genomic surveillance undertaken in Germany, but this changed at the turn from 2020 to 2021 with the rapid increase of infections attributed to the then pangolin lineage B117, which later was then designated, as we've also just heard, as the first variant of concern alpha. And in the subsequent year, Germany experienced larger waves by 3 of the currently 5 designated variants of concern, first being a bigger wave by the variant alpha, which was then replaced by the Delta variant, and at the beginning of 2022 was replaced by the latest variant of concern Omicron, of which we've already also heard about today. So this is then leads us to the context and time of the second example that I'll be showing today, which is a data set of all sequences on GISAID from Berlin in December 2021, which captures the initial spread of the Omicron variant versus the Delta variant. And this is an example of the simultaneous spread of variants with different transmission of properties in the same region with different multiple independent introductions. So going chronologically in time, we can first look at the Heinsberg outbreak in the beginning of 2020. Heinsberg is a district in Western Germany, and the location of it is shown here by this blue arrow. And Heinsberg became a bit sadly popular, or sadly famous in Germany in 2020 because it was one of the first areas to experience a rapid increase in COVID-19 infections very early on. And this started on the 24th of February with the first 2 diagnoses being made. And the first 2 diagnoses were a couple that was already symptomatic for at least 7 days, however, had 9 days prior to the diagnosis attended a big carnival session. And this happened on the 15th of February, this carnival session. And then this carnival session was very quickly taken to have been a potential super spreading event, with the subsequent street carnival happening in the region, facilitating then the further spread of the disease in the whole population. So very early on, there was a regional lockdown implemented in the area, as well as contact measures or quarantine measures for contacts implemented. So the data set that we have from this outbreak spans almost 2 months, and we got the data from Professor Dr. Alexander Dilthey. So it starts with the first sample on the 25th of February, and it goes until the 20th of April, which is the date of the last sample. And in total, we have 52 sequences from this clonal Heinsberg outbreak that we analyzed in VD-Sky, so the method that I've just shown. And considering the context that I've just presented, there are 2 main questions that we want to answer with these analyses. The first one being about the timing of the most recent common ancestor, specifically if the most recent common ancestor of the tree falls before, during, or after the carnival session. So this would basically be about if we find genetic evidence that this carnival session falls into the time period that is spent by the outbreak itself. And if that is the case, we also want to ask if we can actually detect a higher transmission rate for the time in which the carnival session lies, which would then be genetic evidence or genetic support of the super spreading event at the carnival session. So to do this, we set up the VD-Sky analysis like this. So we have one interval for the recovery rate, which we heavily constrain to correspond to a period of infectiousness of 13.5 days. We have 2 intervals for the effective reproductive number, where the first interval ends just directly after the carnival session. So it just about includes the carnival session. And then the second interval spanning the rest of the time that is covered by the tree. For the sampling proportion, we also have 2 intervals. The first one where we set it to 0 before the first sample, and the second one where we heavily constrain it to be smaller than the ratio of sampled versus diagnosed cases in the area. So what we actually did with the sequences that we obtained is that we first excluded the sequences that we deemed to not belong to the real clonal Heinsberg outbreak. And then we used math to align it, all of the sequences to the reference genome. And then we masked this sequence alignment as recommended by the Mayo et al. And then put that into BD-Sky with the population dynamic setup as I've just shown it, and defining an HKY substitution model and a strict clock model. And the result that we obtained from this, you can see here. So this is a maximum clade credibility tree summarizing the posterior sample of trees. And in gray, you can see the node height error bars. So these are the 95% highest posterior density intervals for the node heights. So considering the first question that I've shown about the timing of the most recent common ancestor, we can look at exactly one of those node heights, specifically the one from the root. And here the 95 HPD interval is from the 2nd to the 14th of February, which is directly before the carnival event, here denoted in green, which was on the 15th of February. Now, considering the second question, since we now know that the carnival event actually is within the time period spanned by the outbreak, do we find a higher transmission rate in the interval that includes the carnival session versus the interval that does not include the carnival session? And the results of this you can see here. So this is the point in orange where we allowed the reproductive number to change. And these are the mean estimates that we obtain. So the mean estimate in the first interval is 12.13, and in the second one, 1.77. So taking these results together, what we actually see is that the genetic data supports the superspreading at the carnival event. So this is because the most recent common ancestor of all of the samples falls with very high probability in the 2 weeks before the carnival session, and the inferred reproductive number of the interval that includes the carnival session and not all that much time otherwise is highly increased. So now jumping basically 2 years in time almost, we can turn to northeastern Germany for the second application example, being the December 2021 in Berlin. So what happened there is that in autumn 21 or end of 21, we experienced a wave of quite a few Delta, not quite a few, but a big wave of Delta infections. And at the end of November 21 or start of December 21, this wave was actually starting to decline, which you can see here. So then this was due to the re-implementation of some non-pharmaceutical interventions, which then led to this decrease in case numbers. However, the case numbers then started to rise again very quickly with the introduction of the Omicron variant, which you can see here. So this plot is in German, I'm sorry, but basically all it shows here is on the x-axis the week in 21, and on the y-axis the number of cases from a variant of concern. And here we can see nicely in blue the alpha variant in spring and summer, which was then replaced by the Delta variant with these two wave structures here. And then directly at this peak of Delta infections, which was just starting to decline, we see this purple component coming in, which is the Omicron variant. So the data set that I'll be showing here today starts from the 30th of November, where the first Omicron sequence was uploaded to, or basically about the date from which the first Omicron sequence from Berlin in GISAID is from, and we go until the 31st of December. So we basically span the whole of December 21. And here I have to say that all of the analysis and the workflow that I'll be presenting today is still preliminary work. So this is work that Sunny Urvesti and I have been doing together and still working on at the moment. So all of the results have to be taken with a grain of salt here, but the conclusions that I'll be presenting have been very robust to all of the changes in the setup or in the workflow that we've been doing so far. So here we basically have 1,204 sequences, which we downloaded from GISAID coming from the 30th of November to the 31st of December, which we analyzed in BD-Sky. And considering the context, there are again two main questions that we would like to answer. So the first one being if we can detect an increased transmission rate of the Omicron variant relative to the Delta variant, and if so, how big this difference is. And then with considering this basically starting decrease of Delta infections when the Omicron cases started to rise, another question would be if we actually find in the genetic data the two variants to exhibit different epidemic trends, meaning that the Omicron clusters would show epidemic growth while the Delta clusters would either decline or not really grow anymore. So therefore, we set up the BD-SKY analysis like this, where we have one interval for the recovery rate, which we heavily constrain to be around 7.5 days. We have one interval for the reproductive number, but introduce the scaling factor, which I denote here by R0, which quantifies the relative difference in the transmission of the Omicron variant compared to the Delta variant here in green. We have two intervals for the sampling proportion. We set it to 0 before the first sample, and then we have two different sampling proportions for the two variants. And we also put a strong prior on it to be around 5% for both of these variants. And what we actually did is we start from the sequences that we download from GIS8. We assign pangolin lineages to them using pangolin. We align them to the reference genome using MAFT. We mask them, the mask alignment as recommended by De Mayo et al. We build maximum likelihood substitution trees for all of the pangolin lineages using IQ-tree, and then run MPTP on it to define these genetic clusters, which we use as approximation to the transmission chains. And then using the BD-SKY setup, as I've just shown it, and again an HKY substitution model and the strict clock model, we went ahead to analyze these in BD-SKY, inferring this transmission scaling factor for the Omicron variant. Now this transmission scaling, Denise recently added to the BD-SKY code. So before running all of this analysis, we did quite some simulations to check if we can even robustly infer these transmission scaling factors on genetic data. And here, before going to the results from the data, let's have a quick look at one of those simulation studies. So what we do here is that we just first at the beginning set like a different set of epidemiological parameters that we want to consider, and these we fit to what we actually have for the SARS-CoV have or expect for the SARS-CoV-2 data. And then we use master to simulate trees from these birth-death sampling processes characterized by the parameters that we set. And here we've generated trees that are of quite different sizes and share all epidemiological parameters with each other, except for the transmission rate, for which we have two different groups of trees that we simulate. So there's one group of trees that has a low transmission rate here in green, and then there's one group of trees that has a higher transmission rate here in blue. Then we simulate sequences along these trees, and then again use BD-SKY to re-estimate the trees and the epidemiological parameters to see how well we can, in this case, infer the scaling factor. And here you can see the result of one of those simulation studies. And what we're actually interested in here is this R lambda O, which the true value is 3, which means that the ratio between this blue transmission rate and this green transmission rate we set to be 3. And here on the right, with the 95% HPD accuracy, you can see that actually in all of the replicates that were included in the study, the true value lay within the inferred 95 HPD interval, meaning that we can indeed infer the scaling factor robustly. So these are the results that we obtained from the Berlin data. So here you see a lineage through time plot of all of the maximum clade credibility trees, meaning that we see the number of tree branches which are active in the recovered trees at a specific point in time. Everything in green belongs to the Delta variant, and everything in blue belongs to the Omicron variant. And these are the epidemiological parameters, so specifically the transmission parameters that we infer alongside those trees. So let's first look at the upper right. In the brackets, you can see the 95% highest posterior density intervals for the estimates, and in the main value that I'm giving here is the median of the estimates. So for the reproductive number for the Delta variant, we estimated to be around 1, specifically 1.017. And then turning to the bottom, where we have the transmission rate of the Omicron variant, which is characterized in terms of the transmission of the Delta variant by the scaling factor, which in a mean estimate, we find to be 1.7 for this data. And then taking these two mean estimates together, we can see that the effective reproductive number for the Omicron associated clusters we here estimate to be around 1.75. So what this means is that we basically have a quantification of the initial phase of the Omicron takeover in Berlin at this, so in this specific region at this specific point in time, where we estimate the Omicron variants to be transmitted with a higher transmission rate by a factor of 1.7 than the Delta cluster. So this is in Berlin and during December 2021. And we find the Delta associated clusters to form kind of a stagnant epidemic for the whole time period that the trees span, where we have an R value of around 1, while the Omicron clusters grow with an R value significantly bigger than 1. So with that, I'd like to thank you all for your attention, and of course all of the people who contributed to this work, who helped, and with whom we're working together. And yeah, I'm happy to take any question if there's time.
Thanks, Ariane. Yeah, I think we have time for one question, which I will selfishly ask. So for your Bayesian analysis for that Omicron versus Delta study, how was convergence and how was runtime? Because that's a lot of tips to be running in a Bayesian model. Like I often find when I try to fit one that big, I get real problems ever getting it to converge.
Yeah, so runtime is quite all right. So I usually am able to run these analyses overnight and get the results in the next day. However, convergence was a bit tricky, and mainly due to the fact that we have a lot of very, 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 very small clusters in this data set. So there's a lot of trees that actually are only 2 tips, and these are really, really tricky when it comes to convergence, yes. But other than that, it actually converged very quickly and very, very easily.
Thank you. I think